So good morning. So in the previous class we have discussed the family of probabilistic graphical models as a kind of filter. So filtering through lens, one lens which is the factorization lens and the other which is the conditional independence lens. So think of these two as lenses. So the degenerate cases, the extreme cases are as follows. So we have P, x1, x2, xn, this entire joint distribution could have been specified. These two lenses which is the factorization and conditional independence, both of them only let certain subset of this family pass. So factorization will say in the case of undirected, oh, I will only accept this joint when it factorizes as P of product over all cliques of the phi defined on those cliques of x restricted to those cliques, maximal cliques. Whereas the directed counterpart, the way it filters is a product over all random variables xi, comma the parents of xi of the probability of xi given its parents. And conditional independence talks of the following. Okay, so this is these two are factorization, and the summary with respect to conditional independence is that in undirected, two sets of nodes are conditionally independent given a third set of nodes if the third set of nodes blocks every path from the first to the second. Okay, this is the notion. This is a filter. In the directed case, the problem was a bit similar to the undirected case except for the head-to-head nodes. Okay, this is head-to-head nodes. Okay, so with this understanding, let us understand what the degenerate cases of these graphical models is, the case of these filters is. So one extreme case is that the filter lets everything pass. The other extreme case is that this model passes through every filter. Okay, so two cases. Case 1, case 2, filter lets all P, x1, xn pass, and case 2 is all P x1, x2, xn passes through every filter. So one degenerate case is when all random variables are independent of each other. Where would that fit? Which of these two cases would it fit in? Case 1 or case 2? So I tell you a P such that P of x1, x2, xn is P of x1 into P of x2 into P of x3 into P of xn. That is my P. Is that a case of degenerate filter or a degenerate distribution? degenerate distribution. Okay. So in this case, P of x1, x2, xn equals P of x1 into P of x2 into P of xn. Okay, so this is a case 2. The graph is completely connected. What is that case? Obviously the other one, case 1. The case of filter, completely connected, graph. Filter means, so here in this example you see this is entire family. Filter says I only accept some family, some part of that, some subset of that, some subset of the set of distributions that Px is. So Px is any possible distribution under sun. Then this filter says I will only let some of them pass. But if your set itself is sort of independent distributions, then it will pass through any filter, because all independences are there and the filter is only asking for some independences. I mean, think in terms of joint distribution, right? If I can write this distribution as a product over individual x1, x2, xn, then I can also write it in terms of cliques. If I can write in the case of directed model in terms of independent random variables, I could also write it in terms of, there is no harm in putting conditioning, there is no harm in putting some additional variables. The problem is when you remove, problem is not when you add. So filter will just give you a subset. This is all P, these are only those which satisfy factorization over maximal cliques. This is all P, these are only distributions which have this factorization. This is all P, this is only those distributions where you have the conditional independence. Okay. And we have seen that these are equivalent. This is equivalent to this. You see, in the sense I only intuitively showed. Proof is of course beyond the scope of this. And the undirected and directed, the Markov and factorization are equivalent. So the filter gives you a subset. In the case of graphs as filters, so the graph is completely connected, all families of distributions will pass through the filter, because the graph is not insisting on any independence, and the only difference between directed and undirected, the critical difference, they are different, but the critical difference is this head to head node. We saw in the last class. And this is what makes a directed model not equivalent to an undirected model. Likewise, the one above is an example of a directed model which does not have an undirected counterpart. This is also a critical difference. Okay, if you have cycles in the graph, undirected cycles, you can't come up with an equivalent directed, and if there is a head to head node in the directed graph, you can't come up with an equivalent representation in the undirected case, because a head to head node, we know, knowing the value unblocks, right? Is this clear? And because of this, the family of undirected distributions, they are not the same. They have an overlap, they have this overlap. So overlap will mean no head to head nodes and no undirected cycles. Is this clear? And basically what we mean by D here is a directed filter. U is an undirected filter. You get a subset because of filtering. Okay. Now Markov blanket is precisely related to this conditional independence. So it's a blanket that lets your random variable become independent of the surroundings. I mean, it's a surrounding that makes it independent of the rest of the variables. Okay. So pictorially, a Markov blanket, it says that okay, I have x and I give you my Markov blanket of x, which is a set of nodes, and these set of nodes cut off my communication with the rest of the world. Okay. So now please quickly tell me what you think will be the Markov blanket. I mean, it's there on the board, but I want you to also revisit what we discussed in the last class. For a node in an undirected graph, what will be a Markov blanket? For a node in a directed graph, what will be a Markov blanket? Start with directed. It's intuitive. I mean, this is very intuitive. I would say for undirected, it's super intuitive. So Markov blanket is all those nodes which will block my communication from the rest of the world, which means that every path from me to any other node has to pass through one of the nodes in the Markov blanket. It's literally a blanket, right? Unfortunately, in Mumbai you don't require blankets, but anyone from north, you know, you want to shield yourself completely from the external environment. Okay, so what will it be for directed? What will be for undirected? Every neighbor, right? So if I give you x, I give you x1, x2, all its neighbors, immediate neighbors. And we'll keep seeing this in examples. For directed graphs, what will it be? That will be the trickier part. Set of nodes that D separates the given node from the rest of the nodes, but what will that mean? So, D separating nodes. What will you have to keep in mind? Head to head nodes. That will be the problem. Everything else is fine. So, if you have a head to head node, knowing that node will unblock. So, what will you do? You will also pick its descendants. Okay, so let's say I have x and this is say x1, x2. Now x1 might have another child, x3. It may have some parents as well. What will you pick as a Markov blanket? You will pick x1 and then x1 is not sufficient for x. Our query is x. Will you go up x1 or down x1, or will you go down x, where would you ensure that you are shielded completely? How would you ensure? Is x1 a problem? So does x1 block or unblock? x1 blocks, so x1 is not a problem, right? What will be a problem? The descendants of x1. No, x1 anyways blocks, right? The problem is with descendants of x. Okay, so this is not a problem case. So let me change the scenario and let's say this is x and this is x1. Now this is the issue. X is going to a head-to-head node x1. So if any node potentially in the Markov blanket is a head-to-head node, what will you have to do? You will have to ensure that its ancestors are also picked up. Is that correct? So x1 blocks if it's not known, but if it's known, it unblocks. And because it unblocks, you should also get the information from where it unblocks. So x1 unblocks information from x2, right? So you'll have to do this. You will have to basically walk up the ancestors of x1 as well. So let's just, yeah. Well, that's a good point. It's possible that x2 also shares some ancestor with x. So there are all these subtleties where x2 could have, let's actually do that. x4. Now what will you do? You have to pick x4, of course you will pick. But are you happy not picking x1 even now? Okay, so you will have to traverse up the head-to-head nodes. X3 will also be there. X3 is like a normal, but now you may have to include the parents of x3 as well. See, try to understand, x1 has to be included not because of only x2. It could also be because, here let's give let me do this something else. Okay, so this is a case, and let's say I have x5. So x1 has to be included to block information from x5. So x1 is required, but because you bring in x1, you will also have to bring a baggage along with x1. In the given, yeah, and we will not need you. So in this case you will need. So we will subscribe to the undirected case every neighbor, but here we will say every neighbor plus the ancestors of the head-to-head nodes which are in the neighborhood. Okay, so again ancestors is good enough. Is ancestors good enough? I will walk up from x1 to x2 because x1 unblocks, I will get x2. Is x2 good enough? Do I have to go further up or down? x2 itself might be a head-to-head node, right? So therefore so that's the case we need to consider. x2, therefore we are talking about ancestors. x7. So you have to include x7 as well. So this is the kind of complication with directed graphs. Again, everything is just building upon intuition we have developed in the last class. That's why we spent more time in the last class understanding the basic concept of head-to-head nodes. Remember, the color of what you see on the projection is a combination of the original image and the color of the screen film. So therefore, you need to factor in both. What you see will unblock information between apparently independent random variables. Okay. So we'll keep looking at Markov blanket. Now let's look at examples as well. Hidden Markov model is one of the very famous examples of directed / undirected graphical model. You can look at a hidden Markov model as a directed graphical model, but because hidden Markov models, which are basically a chain, there are some hidden random variables and there are some observed random variables. So these are the hidden random variables and these are observed. Now this does not have any head-to-head node, it does not have any undirected cycles. So you could also treat it as an undirected graphical model. No cycles. Your lab will be based on hidden Markov models. Kalman filters are a kind of hidden Markov model where you have continuous valued random variables. So in the case of hidden Markov model, you have discrete valued array. What is the Markov blanket for a node X? So this is, let's say X. What would be the Markov blanket here? Just the neighbors, because we are dealing with undirected effectively, right? So it's just the neighbors, which means this is a Markov blanket. Now Bayesian networks, they have this, they are directed, but they don't have any directed cycles. The directed graphical models with no directed cycles. You understand what directed cycles means, right? I mean, undirected cycles would mean if you drop the direction on the edges, you would get cycles. But directed cycle means even with the edges there is no cycle. So they should not have cycle. Does it have cycle? This example here, no directed cycles. Okay, but what is an issue with Bayesian network? What is it that probably will not make it equivalent to an undirected graphical model? Head-to-head node. Right? The simplest example I gave in the last class is a Bayesian network. The image color and the screen color, how they influence the color of what you observe, right? So these are the head-to-head nodes. So let's look at Markov blanket. This is X. Tell me what the Markov blanket would be. Actually, this X is not an issue. Let me move this X somewhere else. This is yeah. Let's look at this X. Tell me the Markov blanket. Huh? All the nodes? It's a very good point. If this is X, you will have to go down descendants, right? And then also walk up the ancestors of the descendants because they are head-to-head nodes. Why don't we take In this case, okay, if this is part of a larger network, we'll have to pick all of these. Now in this case, his question is, why not not pick any node at all? Because if you pick one node, you will pick many others. So what's an answer to that? I just pick, what is the Markov blanket of X? The empty set. But then what you are saying implicitly there is that empty set blocks the information from all these nodes to X. Is that correct? So suppose I give you one value here, and now I just give you the value here, yeah, I give you the value here. Is the information to X blocked? So you're suggesting that we can still live with an empty Markov blanket, right? So a Markov blanket is that which blocks information from every other node outside the Markov blanket to the node in X. Right. Now important, now every node, should it include a node in the Markov blanket or not? That's your question, right? So I think the question is, from every other node includes, can it include the Markov blanket? Obviously not, right? Because Markov blanket itself is going to block. No, what you have seen a different view of HMMs. So where have you seen HMMs? So basically HMMs can be viewed as probabilistic transducers. In there you will see cycles, but the graphical model view, there are no cycles absolutely. Okay, coming back to the question, Bayesian network, can the Markov blanket be empty? So I am going to leave this as a homework problem for you. In this specific case, should be all nodes or empty set? Okay. If you had additional nodes here, if I had this, right, if I had an outgoing edge here or an outgoing edge here, then you would have to include all these nodes. So the question is, if in the absence of any other node, why include them? Okay, so an important component of Bayesian networks is something called the conditional probability table. So let us say this is my X, this is X1, this is X2. Okay, so Bayesian network, it is a probability over Xi, the joint distribution will be decomposable as P of Xi given the parents of Xi, right. So specifically we will have the probability of X given X1 comma X2. So if X1, X2 are discrete random variables, you will have something called a conditional probability table. It look like this. So let us say they were binary, X1, X2 and X. So 0, 0 and 0, 1, 0, 0, 1, 0, yeah 1 and 0. So basically you will have as many 2 raised to 3 configurations. Okay, so you can imagine all of these configurations. Now each entry here you can associate a probability. So let us take this example here. You can associate a probability with this, which is the probability of X2 equals, X equals 0 given X1 equals 1, X2 equals 1. So this is called the probability associated with this configuration. So now if you add one more column, you will get a conditional probability table. You will have to associate probabilities for every row. a simple thing, I mean it just has a name. And let's also relate this to logic. So all of you have done a basic course on propositional logic, right? Logic, you had a course, yes or no? Right, so you might have seen things like this. These are all ground predicates. First order logic as well, obviously you have done. So these are ground predicates. So Anne, Dorothy, these are, let's say, people, and so the mother chromosome of Dorothy is influenced by the mother chromosome of Anne and the parent father chromosome of Anne. So so Dorothy is influenced by Anne, and Anne, blood type of Anne is influenced by the chromosomes of Anne, okay. And there's another person, Brian, there. So we're basically talking about Anne, Dorothy, and Brian, and you're told that Brian has some parent chromosome, father chromosome, and Brian also has some mother chromosome. So you're given some ground atoms and the influence between these. So and the idea here is how a child's chromosome is affected by those of the parents. The parents in themselves have also their own parent chromosome, ancestor chromosomes influencing their father and mother chromosome. Okay, that's what we are trying to capture here. Now, could you think of what graphical model this represents? This by itself doesn't have any probabilities, right? But now you can associate probabilities with each of these. There is a degree to which a parent chromosome influences the chromosome of a particular person. Okay. So, if you were to put this in a graphical form, this is what it's saying. The blood type of Anne is influenced by the mother chromosome of Anne. The mother chromosome of Dorothy is influenced by the mother chromosome of Anne. Okay, so, and also by Brian. So, let me just highlight the sections. So, this and this. So, Brian is the father of Dorothy, Anne is the mother of Dorothy. Okay, so the relation is here, mother, father, okay, and because of that you have these influences represented through a Bayesian network. Now there are advanced courses where you could talk of abstracting from grounded predicates to the first order logic itself. I mean, why do you need these two separate, MC Dorothy in terms of its MC of Anne and PC of Anne, and PC of Dorothy in terms of MC of Brian and PC of Brian? You could in general talk about father and mother chromosomes influencing that of the children, right? So in general you could actually compact this network. So you have something called Bayesian logic programs where which are generalizations of Bayesian networks, but again that's too advanced to talk about right now. Okay. Okay, and you can have corresponding conditional probability tables at these nodes. You can also have multiple hidden states, generalizing hidden Markov models. So multiple hidden sequences here, right? So if you restrict those to a single hidden sequence, you get something you already know, which is the hidden Markov model. And then you can have Markov random fields, you can have conditioned random fields, but all of them are characterized by exactly this form. So these are undirected models where you look at maximal cliques. So in this case the cliques happen to be, this is a clique and this is a clique. So what you are doing here is you are decomposing a clique probability into two components of the clique. One which is xi yi and the other is yi with the interaction with its neighborhood. Okay, so what you should have ideally had is a big clique with yi plus 1, say yi minus 1 its neighbors and xi. Now that has been decomposed into two parts. One, the neighbors of y, the hidden, this is the hidden layer, and you are separating that from the observed layer. Okay, then conditional random fields take it further. They say that we can condition on the entire X. So again, I mentioned about conditional random field when we talked of generalization of logistic regression, but I will not. These are really examples for your understanding. So now we will quickly look at how can these graphical models be trained. So they typically use maximum likelihood and variation and their variants. So basically you will train using maximum likelihood. There are others also. You can do margin maximization, you can do minimizing number of errors and prediction, very much like perceptron did, and correspondingly you have different techniques. Like for example, if you want to look at minimization of number of error and predictions, you can look at voted perceptron, the variant of perceptron. But what we are going to focus on is just these two, maximum likelihood and expectation maximization, and again I will illustrate for very simple case, the simplest amongst those. So this is the training part. So we will try and do the simplest illustration for graphical models using the training part of it, using hidden Markov model and then Gaussian discriminant analysis, which are very simple. So you will see that Gaussian discriminant analysis is a very simple example, even a simplification of Kalman filter. And we will then look at EM algorithm. So we will begin with learning under complete observations. I am going to erase this and focus on our simpler problem. So we will start with hidden Markov model. Again, your assignment today is going to be at least 3/4 of it is on hidden Markov model. As I said, you have bunch of observations x1, x2 and so on, xk, and you have these hidden states y1, y2, yk, ym. In the case of hidden Markov models, we are looking at x and y being discrete random variables. So each of these x can take some discrete values. In the case of your assignment today, these are words. So imagine that you observe some sequence. I saw a boy with a telescope, or natural language processing, that is going to be an example. So let us say the words I see a natural language processing. So these are the words I observe. Now you understand what parts of speech tags are. What are parts of speech tags? Adjectives, nouns, verbs, etc. What is a part of speech tag of natural here? What is natural? Adjective, right? So the y's, each yi could come from bunch of tag, could have one of these tags values t, n, and this could be an adjective, this could be a noun, something else could be a verb. The xms, the xis could be one of these words. So large vocabulary. So let us say a dictionary, your Oxford dictionary, your Cambridge dictionary, it will be very big. Okay, so what you have two things here. You have a transition probability from x1 to from one state to another state, where each state can take one of these tags. Now why should your natural language processing have a particular tag sequence. What is language here? Just to complete the whole. Language is noun. Okay, so we expect that this will be an adjective, this will be a noun, this will also be a noun. Now, this is a specific form of noun. Let's keep it simple, noun here. Okay, now in general you expect adjective, noun, and not noun, adjective. There are some patterns you expect. We have discussed this earlier also in the case of auto completion, right? And in fact, we have a complete tutorial problem on auto completion today, which also you can have a look at. Okay, so now if I want to just learn what the tag sequences are, what the transitions of these tag sequences are, what is the probability of T1 given T2, right? What is the probability of transitioning from an adjective to a noun, what is the probability of transitioning from noun to a verb, and so on, and what is the probability of natural being an adjective, right? Can natural be some other part of speech as well? Some words have multiple parts of speech. So natural probably is just one part of speech, but something like can, right? Can be an auxiliary verb, helping verb. Can also be a noun, a milk can, for example. So what we will have here are probability of a particular word that can be emitted from a particular part of speech tag, and the probability of one tag going to another tag. These are the two things. Okay, so this transition is the probability of transitioning from one tag to another. This emission is the probability of emitting a particular word given a particular part of speech tag. So let's say I give you some training data, and in your lab today you will be given some data where you are given words and their parts of speech tag. So if you do a maximum likelihood here, right, max, so what I want to do is P of W given T and P of T given Ti given Tj is argmax. I view this as a probability distribution, decomposed using hidden Markov graph. So that's argmax over all the training examples of probability for each training example, product over all the nodes in that graph of probability of Wi given Ti, probability of Ti given Tj. Right, if you are going from Ti to Tj, you can make it Tj given Ti, depending on Tj given Ti. So this is the maximum likelihood problem. Maximize the likelihood of observations as per the model distribution, things you have been doing throughout the course. But it turns out that the estimation is very simple. I mean, for all the hard work of writing on this maximum likelihood, the estimation is very simple. Okay, so this is the argmax, these two correspond to the argmax of the likelihood, and why will require a little bit optimization trick, but then I will not get into that. And now let us look at intuitively what these two expressions are saying. It says the maximum likelihood estimate for probability of Tj given Ti is just the fraction of times in the data set that Tj went to Tj came from Ti. The fraction of times in which noun came after adjective is the probability of transitioning from adjective to noun. Is that intuitive? the fraction of times, it's just a relative count. Instead of absolute count, you just dividing. So that's the first expression, the fraction. Emission probabilities, can someone explain? That's as obvious as transition. What is the probability of natural given adjective? It's the fraction of times I have seen natural coming from adjective. Now the fraction, the denominator is probably the only thing you have to be careful. Numerator in both cases is count. In denominator, when you are transitioning from adjective to noun, you will say the fraction of the number of times noun came after adjective divided by the number of times adjective was seen at all. Okay, so let me write that in plain words here. So probability of noun given adjective is number of times noun adjective was followed by noun, that's the count part, divided by the number of times adjective was seen at all. This is the number of times adjective was seen at all, and the numerator is the number of times adjective was followed by noun. That's it. Is this intuitive? But that's what likelihood maximization will do. Likewise for emission probabilities, the emission of word given the tag, probability of natural given adjective is number of times, again natural was produced from an adjective divided by number of times adjective was seen at all. Okay. So it turns out for hidden Markov model these estimations are very simple when the data is completely observed. So I observe natural, I observe language, I observe processing, I observe the tag of natural, I observe the tag of language, I observe the tag of processing. Now the trick is if some of this gets missing. So let's say that my data gets corrupted, I am lazy in annotating, I am not able to get labels for each of these and my noun gets missing. I mean I don't know what the part of speech tag of language is. Then what do you do? So then you have EM. How many of you have studied EM already? So those who are taking the speech course, right? So but in the interest of others I'll explain EM in a much simpler setting. Okay, so EM is when some TIs are not observed, and unfortunately EM will require a lot more heavy lifting. I am going to illustrate EM in a much simpler setting. So I am going to illustrate this in the case of something simpler, which is Gaussian discriminant analysis. Now this is also a graphical model. Okay, so this is also a case of a directed graphical model, which can be viewed as an undirected graphical model if you wish. And as shown on the board, what is this graphical model? This says, and you can contrast this with HMM. You have X and you have a Y. Okay, a very simple graphical model where this Y is one of K classes, X is some observation, this could be points in a two-dimensional space, X could be a vector where you can say phi 1x, phi 2x, and each of these could come from different classes. So for example I could say these points, these x's are coming from C1 and another set of points are coming from C2. It's a simple setting. Now you can have k classes. Now all we are saying in the case of Gaussian discriminant analysis is that these points for C1 come from a Gaussian distribution for C1, these points for C2 come from a Gaussian distribution for C2. Okay. I mean it's very often the case that you look at this, right, in 2D Gaussian this looks like, this looks like Gaussian, may not be always perfect fit, but that is the assumption made here. Okay. So and these are like mu1, mu2 are vectors, sigma 1, sigma 2 etc. are covariance matrices. Now if you assume that every point is generated using exactly one of the classes, and that is what we have shown here, these points come from C2, these points come from C1, and then if I ask you to, okay, tell me how the separating surface will look like your classification problem, what will that classification surface look like? I mean I have said it is quadratic, but then you can try and write down the expression. The expression is probability of C1 given phi x equals probability of C2 given phi x, let us say for 2 class case, and the claim is that the separator will be like this, it will not be linear, it will be elliptical. Okay. C1 given x, now we just mapped x to phi x, think of this phi as a potential, as a feature function, which is in graphical model parlance it is just a potential, but let us just write it as p of C1 given x as, so you know the form of multivariate Gaussian, have you studied the form of multivariate Gaussian? So what will that look like? 1 upon determinant of sigma here, what else, under root 2 pi, the whole thing under root 2 pi, right, into exp of minus x minus mu transpose sigma inverse x minus mu, it will be 1 by 2, and here you will have mu sigma 1 for class C1, sigma 2 for class C2. Okay. This is a very simple graphical model, and you could think of this as a very simple Kalman filter, square root of determinant. Pardon? Right, 2 pi raised to d, n in this case, yeah, you mean n is a dimension, right, n by 2. Okay. So where we are assuming that this x or phi x is an Rn. This is for example 2 dimensional. So it turns out that if you just equate the equations, equate these two, probability of C1 given x and C2 given x, then if you take logs, basically what will you get? So if you take logs of this, for both classes and equate them, what would you get? Minus phi x minus mu I transpose sigma 1 inverse, let us say mu 1 phi x minus mu 2. Okay, so minus or plus phi x minus mu 2 transpose sigma 2 inverse phi x minus mu 2, you will get some expression like this is some constant independent of it will be term independent of x. Let us not call it constant, terms independent of x. Okay. So this is this is how it look like. This is a quadratic equation and therefore you get a quadratic separating surface. It is called quadratic discriminant analysis. Now if I wanted to do maximum likelihood here in this setting, again the same graphical model equation, probability of x given y, I want to maximize. The maximum likelihood expressions are going to be very simple. What are those going to be? What do you think will be MLE estimate? Most intuitive, which is sigma mu I will be the mean of all points that belong to that class. Mu I will be xi belonging to class Ci of phi of xi divided by the size of Ci. That will be the maximum likelihood estimate, because it is basically every class being treated independent of the other classes. X only depends, x is independent of other y's given this y, because it is not even like this is the simplest case. In hidden Markov model you had multiple y's, so different values of y will not influence, only the class corresponding to that example will influence the probability of the value of mu I. Okay, you can likewise do sigma I also. So that MLE estimate is simple, and this is what Gaussian discriminant analysis looks like. As I said, it is quadratic surface. Okay, so here is the maximum likelihood estimate. You can set the gradients to 0 for both mu I and sigma I, and you will get these expressions. Mu I is the average of all the phi's belonging to that class. Sigma I can also be obtained as a sum of outer products between the phi shifted by mu. And finally, you will also need the probability of y belonging to each class. Okay, so that is a prior probability, and that is nothing but the fraction of examples that belong to that class. Okay, see, all the three updates are very intuitive. Mean of points belonging to a class, outer product between vectors shifted by the means belonging to that class, that is covariance, and the third is fraction of points belonging to that class. So I am trying to only appeal to intuition. The derivation is there in the slide, which is not very important in this case. Okay, so you can do this Bayesian estimation. This, as I said, this is optional. You can also put some prior on the y's. You can do map estimation, but I am leaving this as optional. And in tutorial 8, I have said, well, what happens if shared covariance is used? Suppose you have a shared covariance matrix sigma, what will happen? Sigma is not, so in this case, these two sigmas were different, sigma 1, sigma 2. Suppose I make them both sigma 1, sigma, okay. Will this separating surface be quadratic or linear? We will have a linear separator, this will become linear. Exactly. So if you assume a diagonal structure on sigma, you will get k-means. It's something like k-means, not exactly k-means. But there is a difference. Now k-means doesn't even, you don't even know what the C's are. So we are coming to k-means. We are coming to the equivalent of k-means. So this you can look at a tutorial. So linear discriminant, this is how it looks. Instead of quadratic, you will have linear separator. But now let's assume that instead of having green and blue as the colors for the points, I remove the coloring of the points. Okay, so I tell you the same, the problem is the same, but now the coloring of the points is removed, and indeed they look like two Gaussians sitting there, but nobody tells me that there are two, that this point belongs to C1, this point belongs to C2, nobody tells me that. This is exactly the case of clustering that you have seen, but now we are going to view it from the point of view of the simple graphical model. Okay. So I want to learn the probability of x given y, the probability of y, where I can maybe make use of the same distribution assumptions, but the coloring suddenly disappears. Okay, this is learning with incomplete observations. In the case of hidden Markov models, the same thing is, I tell you this is adjective, but I don't tell you the part of speech tag of language. So natural is adjective, language I don't know, processing I don't know. How do I deal with incomplete observations in both cases? So I will quickly look at mixture of Gaussian's case. So the assumption is violated where phi x is generated not using exactly 1. Your probability of x is a sum over all the classes. So you have k classes of the probability of the class into the probability of x given the class. It's simple, again, just done marginalization, right? Use basic rules of probability. That's all I have. I have the probability of a point. I don't know the probability of x given Ci. I will assume that x given Ci. I'm sorry, I made a small mistake here. Yeah. Forgive me for the mistake, but this is x given Ci. Obviously, the graphical model was x given Ci. Just here it's x given Ci. Because that's the directional model we are using, x given Ci. Okay. So I'm giving these forms, x given Ci, the probability of generating a point from class 1 or class 2, but I don't know the value of mu1, I don't know the value of sigma, I don't know even the value, I don't even know which point belongs to which class. So that's the model I'll adopt, and here I'm going to talk about maximizing likelihood. So what I'm going to say is argmax over mu1, sigma 1, mu2, sigma 2 and probability of class of the likelihood of computed across all the examples. This is the problem. Okay, so we are not told that the point belongs to exactly 1. So we'll use this assumption, but here we'll have a mixture. Okay, this is probability of C given a particular, now we'll start using Z instead of C, because C was to mean class, Z means a hidden mixture component, a hidden class. So Z is used as a hidden class, C was used as an observed class, just to distinguish between the two. Okay, so exactly what I had written in the previous slide, and for next 5 minutes we'll just develop on this. This is the idea. So it's called mixture model, where you have mixture from different components, each of the components is hidden and the mixing components are hidden, each of the components has variables, parameters which I don't know, but still there is an intuition, I mean the clustering intuition again, right. So clustering, I would say, well, this one cluster, this is another cluster, but now I want to do it in a more principled manner, where I have this simple graphical model, x generating y, sorry, y generating x. The hidden class is generating the points. Please tell me what is the probability of the hidden classes, what is the probability of generating the points, what the parameters will give me the probability of generating the points. Okay. So this is a finite mixture model, probability of phi x is this first part often in literature is also called, is just referred to as pi I. Pi I is a mixing component. Or mixing weights. So we want to be able to learn the mu i's and the sigma i's that characterize the probability of x given z I. Now it's not that this mixture will remain a Gaussian. Each of this is a Gaussian. X given C1 is a Gaussian, x given C2 is a Gaussian. But the moment I start combining all of these, it will not be a Gaussian anymore. A weighted linear combination of Gaussians is not necessarily a Gaussian. Is a product of Gaussians always a Gaussian? Product of Gaussian is always a Gaussian, but not a weighted linear combination. Okay, so that is the issue. So we already done the supervised setting, but the question is, what happens if incomplete data we don't have the zi's. Okay, so now the idea is, I mean the algorithm will turn out to be very simple, and the idea is that you want to maximize this log likelihood of this p of x, right. Now if you take log of this summation, basically you are finding log of this summation. Does log distribute over summation? So far we have been doing log of product, right. So log of product is okay, so log of product is summation of logs, but the problem is that log of summation, what do you do? Because of this mixing component we have the issue, right. So the rest is basically just the notation where we have developed so far, the probability of x given zi, probability of y equals zi. So log cannot be distributed over summation, what do you do? So do you know some interesting property of log that can be used? Convex, somebody said convex, is it convex or concave? How does the log function look like? Concave function? And what do you know about concave functions? From your basic calculus. Log of summation alpha I x ti, and let us say the alpha i's sum to 1, alpha i's are all between 0 and 1. What will this be? Less than equal to summation over I of alpha I log of ti. Right, this less than equal to is basically saying that if I take 2 points and connect them using a line segment, the line segment will, sorry, this is greater than, right, this is greater, this is greater than. So we are saying that the greater than equal to saying that the curve will always lie above a line segment joining 2 points. Can we make use of this? Okay, that is the property we will use. Okay, so what we will do is, we will say that this log of summation, where the first component, the pi's, do the pi like the alphas, do the pi's sum to 1? Pi's are these, right? Everything that is essential I am written on the board. The pi's are summing to 1 because by design they are mixing components. This will sum to 1 across all classes. So this is my alpha, this is like my alpha L. And the second component is like my TIs. Think of this whole thing as TI. Okay, so I know that this is greater than equal to summation over pi I log of Ti. The Ti is that entire expression. This is the basic property that is used in the EM algorithm. Instead of trying to maximizing this, you try and maximize the lower bound. Okay, so the details of EM and also things related for the lab we will continue into the lab session today. The lab session will have some discussion because I'm trying to pace it so that I don't rush through a topic. You can implement. We will continue the class as you progress in the lab.